Okay, let's get started. So welcome everybody to the ultimate lecture on the first SNAPP summer school on Stein's method for queuing approximations. Thanks for sticking around for the whole course. And This is the first time we've run a summer course. So if you have feedback, we're happy to hear it. Please feel free to email me or the SNAPP email address, which you can find on the SNAPP website, if you sort of have feedback about the sort of course structure and anything along those lines. Okay, and so without further ado, Anton,
Okay.
let's finish.
Thank you, Zeev. To be honest, this flew by really fast for me personally. I know maybe some points were slower for others. All right, so today I've got my 90 minutes, and I've learned that 90 minutes isn't really a lot of time. It flies by fast. So today, what I really want to cover is I want to finish the GG1 workload example. And just to give you an idea of what else is needed when we go beyond exponential primitives to, say, general model primitives. And then in the remaining time, a quick illustration of fluid/mean field approximations. And at the end, maybe I'll spend some 5-10 minutes just talking, being forward looking and talking about where all of this theory is in the field and what are some opportunities. Okay, so to recap, we were looking at the workload process, which I called Z of t. And Z of t, the workload, was composed of the scaled workload. Sometimes it's called the virtual waiting time, hence the V, and the residual inter-arrival time, or the residual arrival time, where delta, this is 1 minus rho. Rho is the utilization, lambda times the expected service time. And what we basically showed is that the generator of this process Z applied to any function where the generator is defined in this way. Minus f of z over t. This is the partial with respect to x. Part here. So basically, I said that this object is a piecewise deterministic Markov process, meaning that it is deterministic almost everywhere, except when the timer hits 0, then a jump happens. Okay, those are the only random components of the process. So as long as, and here this is z x bigger than or equal to 0 and residual arrival time strictly positive, because we adopted a right continuous version of the process. So as long as there is workload in the system, the process will be decaying, or the workload will be decaying at a rate of, in this case, delta, because the unscaled workload decays at rate 1, the scaled workload decays at rate delta, and this will impact the first coordinate of our function. And then all the time, we will have the residual arrival process, residual arrival clock decaying, so this will impact the second coordinate of our process. And this is the infinitesimal generator. And I ended last class by saying, well, we're used to the generator giving us all the information about in particular, the stationary distribution of the process. But then I looked at this and I said, this doesn't seem like it's giving us all the information. In particular, like, there's nothing random here, right? Okay. There is no randomness whatsoever. There's no random variable here. So something must be missing. And then to give you an appreciation for what is missing, why, and how to, what is the systematic way to think about it, I want to take a step back and I want to go back to the very, very first class when we talked about Ito's lemma. And I want to talk about what is it that makes these generators so important or so useful. Okay. So if, and let me stick to the perspective that the generator is always defined to be this limit, although sometimes that's not the way it's defined. Okay. So if it's always defined to be this limit, and we look at this limit, like what is this? This is really the time derivative, of, this function, but the time derivative with respect to the expectation. So to be more precise, it's like d by dt, expected value z, f of z of t at t equals 0. That's the generator, right? And we can extend this. There's nothing special about t equals 0 because essentially this little z in the subscript is basically saying we're conditioning on our location. So we can extend the concept of a generator. We can condition on z of s, for example, and look at the time derivative at t equals s. Okay, so that's going to be the generator. All of this goes to say is that for example, for CTMCs, we have this very nice property, and this is Dinkin's lemma. X of t. Well, let me stick to the notation CTMC. Let's imagine that Z is a CTMC. Z of t minus expected value Z f of Z naught equals expected value sub Z 0 to t generator of the Markov process applied to the function ds. All right. So the generator is important, not because this has some inherently interesting properties, although it ultimately does, but the generator is important because of this. This is why it's important. This is again Dinkin's lemma. In the context of Ito diffusions, we have something very similar. We have something identical actually. That we called Ito's lemma. Why is this important? Why is this special? Because now, if you initialize the initial condition to have the stationary distribution, the left-hand side equals 0, and we recover what I kept referring to as the BAR, or the stationary equation. Okay, so it's really this magical, wonderful property of the generator that makes it so significant. Now let's come back to our example and let us look at the generator we derived. Question. For GG1 workload, is it true that basically this same thing holds? And the answer is no. And you can tell by my entire prelude to all of this that this isn't enough. But why isn't it enough? The answer is because unlike in continuous time Markov chains, we have this piecewise deterministic, well, yeah, we have this piecewise deterministic structure, and we have the jumps when the clock hits 0. And you'll note that I left out those those points when the jumps happen, I left that out of the state space when I was defining the generator. And I said, well, it's right continuous with left limits. And so we never really reach those points where RA equals 0. We don't reach them, the Markov chain is never in them, but it does approach those points. So they are important. And so I want to augment this relationship. What I wrote in blue is not true, but if we augment it a little bit, it will be true. Okay, so this is the BAR, say for the GG1 process. And first off, no randomness. Okay, suppose we have a function of our workload process, and suppose for the time being that it is sufficiently regular. It's as differentiable as we need it to be. And I want no randomness, no expectations. I want to express this as, say, some fundamental theorem of calculus type identity. Well, we have PDMP jumps when arrivals happen. And let's let A of t be the counting process, or be the simply arrival process. So A of t, this is number of arrivals on 0 to t. Okay, so now we take this object and let's integrate from 0 and let tau sub m be the time of the mth arrival. Also, I'm going to make this assumption for simplicity. Assume that the probability, so U was my inter-arrival time distribution. U is inter-arrival time distribution. I'm going to make the assumption that we do not have any batch arrivals, right? That there can be at most one arrival at a time with probability 1. Okay, so if we look at this object, and by virtue of a telescoping series, we look at time from time 0 until time tau 1. Now, tau 1 is special because actually tau 1 happens to equal the residual arrival time at 0. So I'm just making a connection. Okay, d by dt f of d by, let's say, ds f of z of s ds. Okay, this first integral is the fundamental theorem of calculus. Why? Because it's a determinist. The process is deterministic from 0 to tau 1. Now at tau 1 something happens. A jump happens. So I'm going to denote z of tau 1 as the post-jump state, and I'm going to call z of tau 1 minus, this is the pre-jump state. Okay, and let me add in here this nice indicator that tau 1 actually happened on or before time t. And here I would technically need to add the truncation by time t. Okay, so then at time tau 1, I do this again. I say, okay, now from time tau 1 until the second jump, and of course I should truncate minimum t. I do d by ds, f of z of s, ds, and then the jump again. So you see, my point is that we've broken down this process into the deterministic parts and the random parts. When we were deriving our infinitesimal generator, we were looking at the time derivative of the of the process on the deterministic components. So this time derivative actually is exactly what we've derived over here. And what we are starting to develop, what we're seeing is it's not enough to know the time derivative on the deterministic part. We also need to account for these jumps. These are the random ones. So I'm going to introduce some notation. I'm going to define this to be another way, delta f of z of tau 1 minus. So this is like the jump, post-jump state minus pre-jump state. And if we carry this up procedure out, we get the integral from 0 to 1 d the time derivative, but the time derivative actually happens to be what we've derived, our generator. So let me write it down here. So it's from 0 to t, not 0, 1. X of s is positive, partial x f of z of s minus partial with respect to the second coordinate f of z of s ds. That's the deterministic component. And then we have the jump component. Sum m goes from 1 to infinity. The jump at time m or tau m. And we have to include the indicator that tau m is less than or equal to t. But writing out this infinite series representation is going to be very bulky and cumbersome. So I'm just going to write this simpler. This is going to be the integral from 0 to t, delta f of z of t minus, s minus, dA of s. So A of s is the arrival process. I think mathematically, this, what I have circled, is always defined in terms of the infinite series, as far as I'm aware, because otherwise this doesn't have meaning, but the infinite series does have meaning. Okay? Okay, so we're done. And now we've observed that, okay, we've written this out using the fundamental theorem of calculus. We have the deterministic component, we have the jumps. And now this makes more sense because, okay, all of the randomness is encoded in the jump term. And now we are free to take expectations with respect to the steady state distribution. And if we do that, let z naught come from the stationary distribution and take expected value to get. And I'm going to leave a little room for the assumptions or the conditions that need to be verified for us to be able to do this. So first of all, I take the expectation with respect to the left-hand side. And for this to be 0, I need, so conditions, I need f to be integrable. That's non-negotiable. Then I take the expectation of this thing. And ideally, I would like to interchange the expectation outside the integral, and I would like to bring it inside the integral, because when I do that, I can use the stationarity of the process and I can get rid of the time variable, right? So what I need there is Fubini-Tonelli condition. Okay, something like, basically, I'm not going to write it out. I don't have enough space, but the integrability of these derivatives, right? Um, I get the BAR. So negative delta indicator x bigger than 0. partial x f of z minus partial second coordinate f of z plus expected value 0 to 1 delta f of z of s minus dn of s, oh, dA of s. And the whole expectation here equals to 0. This is the BAR. So it has our infinitesimal generator bit plus a jump term. Before I move on, if you don't understand this, or if you have some questions, if you don't fully understand this, you need to ask now, because the rest of today won't make sense to you one bit. Okay, so let me copy something down as you think, whether you have a question or not. I encourage you to ask. So we have negative delta expected value indicator x is positive minus expectation f of z plus expectation 0, 1, 0 to t. What I implicitly did here was I made the bar for t equals 1. It doesn't matter, the value of t doesn't really matter because it's a stationary equation, because the integrand is going to be independent of time. And so you can just rescale everything by dividing by 1 over t. And the 1 over t will cancel out the term up top. And the same thing will happen to this thing. Okay, so let me just say t equals 1 without loss of generality, delta f of z of s minus dA of s. Okay, we have 3 terms, 1, 2, 3, but I'm going to simplify them even more because I want to take a step back and ask ourselves, what are we doing? Why are we doing this? I remember our original goal is to derive a diffusion approximation for the workload part, right? So let's say I only care about the workload. I don't care so much about this second coordinate. So I'm going to pick a function f of z, which is really f of x and RA, to just be a function of the workload component. And then the BAR simplifies, or so it seems at first glance, really. That's what I should say. To this. All right. Now we have one. Well, let me not label them. Okay. So let's remember our usual procedure, right? So we've written out the generator, but now I've given you the BAR. Instead of the infinitesimal generator, I've given you the BAR, but I'm going to say, okay, don't worry about the presence of the expectation, because when we do generator comparison, we take expectations at the end anyway. And let us just see if we can derive a diffusion approximation, a second order differential operator. Let me simplify notation here. This is actually f prime of x. And this is x of s minus. Okay, so where is our diffusion generator hiding? We only have the 2 terms, which makes life easy. In our first term, we see, oh, okay, I've got an f prime of x. This is like a first order term. So I have some negative drift. This is basically saying that as long as there is workload in the system, the workload will be decaying. And so my diffusion process should have a negative drift as long as it is bigger than 0. That makes a lot of sense. What about this thing? And notice I haven't said anything about it yet. I've been keeping it in this weird integral form, but that's for a reason. Okay. And this term is where all the magic is and all the difficulty, perhaps. Now, there are two ways to go about thinking of this. If you, number one, know Palm calculus, or you don't know Palm calculus. I've been lucky because so this topic is something that Zeev and myself have been working on together. I fit squarely into this realm. I don't know Palm calculus, and it's a beautiful theory of point processes and such, but it's just such an overhead to learn it that my by my estimate, I don't know, I would say the vast majority of people in our field probably don't know it. Okay, they know of it, but they don't know it in detail. Zeev was squarely into this field, and I think having one of us in each of these buckets really helped. All right. So if you know pump calculus, what I'm about to say is it's not even using like 10% of the power of the theory. This is the most basic, simplest example that you can apply pump calculus to. But then you take a look at this and you say, oh, well, A is a point process, it's a renewal process, and this is just the expectation at the renewal time. So this is like an event average expectation. So this is just a palm expectation. And oh yeah, I can take that palm expectation and I can crank it through some well-known machinery, if you know palm calculus, and you can express this object, which is expectation with respect to event times, as the more familiar to us object of the expectation with respect to time averages. Right. So the biggest difficulty about extracting the generator, a diffusion generator here, is that we look at this term and we're like, what exactly do I do with it? How exactly do I get a diffusion generator out of this? Because I'm not used to seeing these expectations with respect to renewal processes. So if you're in this bucket, which is me, I was always trying to basically, I'm say I respect the fact that palm calculus exists, but I would love for there to be like an elementary, very simple way to digest what we're about to do. And that is the philosophy behind the exposition that I'm going to show you today. Oh boy, half an hour went by. Okay, so let us focus on the star term. First of all, when a jump happens, what happens to the workload? Let's answer that. So at jump epoch t, x of t is whatever workload we had prior to the jump. And this, by the way, is the limit as epsilon goes down to 0, x of t minus epsilon. That's the rigorous definition. Plus the service time. Okay. And to make a distinction, let me write S of t because so S of t equals um, work brought by an arrival at time t. If there is no arrival at time t, S of t equals 0. So this is kind of like a process basically has delta masses in some sense. Okay, but this is indisputable. So whatever we have post-arrival is pre-arrival plus the work brought in by the customer. So if we focus on this and I ignore this scary bit of the arrival process and I just focus on understanding the jump, I can actually do that. It's not that difficult. Let me switch back to using t's. Okay, expectation 0, 1, f of x of t minus plus delta s of t minus f of x of t minus dA of t. Okay. So now I say, oh, okay, I can do this. Let me just do Taylor expansion around this. And this is going to be expectation, integral 0 to 1. So I've got delta s of t, f of x of t minus dA of t plus 1/2 delta squared, 1 s of t squared, f double prime x of t minus dA of t plus 1/6 delta cubed s cubed of t. And this is f triple prime at some c. So I'm just going to use c to denote this dummy term, which corresponds to the Taylor expansion remainder term. And as usual, I'm going to treat the third order stuff as error, but the first two orders are not going to be error. And the nice thing is, so let's do this term 1, 2, and I'm not going to talk about 3 because that's error. 1, can I simplify this further? Well, the service time of the customer that is incoming at time t is independent of the workload before the arrival, right? That's great. So basically this S is independent of the workload before the arrival. Does it mean I can pull this out of the integral? Or does it mean like that the distribution of this is invariant in t? The only thing that's preventing us is this dA of t. And I'm going to write it out one time using its formal definition, and then you can see what's going on. So delta, expected value, sum goes from 1 to infinity, s at the arrival epoch, f prime right before the arrival, x of tau m minus dA of t. And whoops, that was just me on autopilot. Indicator that tau m happens before time 1. And now we can make more sense of it. Again, the workload brought in at time tau m is independent of the workload before the jump. And all we have here is the indicator that the mth arrival happened before time 1. In particular, this is just saying, was the arrival quick enough to happen before time 1? If it did, the workload brought in at time tau m is independent of this fact. Okay, so this you should be like, oh, Wald's identity, something like that here. Okay, this typical, or the stopping time property. Good. So now we can take this out. Delta expected value just of s. Expected value sum m goes from 1 to infinity f prime. So the rest stays the same. In particular, I cannot repeat the same trick with this workload because the workload right before the jump happens is certainly very much dependent on the fact whether the jump happened before 1 or not. Okay. So I cannot do anything about this term except I'm just going to write it in terms of the integral that we're used to. 0, 1 f prime x of t minus dA of t. Okay, good. Now we look at term number 2. Same story, right? Exactly the same story, except we have f double prime instead of f prime, and s squared instead of s. So term number 2 equals 1/2 delta squared, second moment of the service time, 0 to 1, f double prime of x of t minus dA of t. Okay. Term number 3, we're going to treat as error. Let me give you a quick argument why we can treat this as error without any extra fancy machinery. Suppose we know that the f triple prime, the third derivative, is bounded uniformly. So it's uniformly across all possible states is bounded by some constant. So we can take the norm of this thing and we can pull it outside of the integral. If we're just interested in bounding this, not computing it. If we pull out the norm, then we have this s cubed term. But by the same logic we just applied, the work brought in at time t is independent of the fact that the arrival happened. So we can also pull out the s cubed. Okay? And all we're left with is, if we ignore these two quantities, this integral just represents the number of arrivals to happen from 0 to 1. And this is basic renewal theory at this point. Okay, that you can bound the expected number of arrivals to happen from 0 to 1. The machinery is there for you. There isn't anything crazy that needs to be done. So the third term is truly boundable as long as we know that this thing has some kind of finite norm. But if we say, okay, let me just backtrack. We said, okay, so this contributes to our diffusion approximation. We were not sure what to do with the jump term, but we went in and did what we could. That is, derive the expansion. We derived the expansion. We've simplified 1 and 2. Now 1 and 2 look very similar, right? They have some term involving the first and second moment of the service time, and they have this expectation or this integral term with respect to the jumps. We wish that this could just be replaced by the expectation of f prime of x, right? And maybe something else. Because that thing on the right-hand side we know how to deal with. That would contribute to the diffusion approximation. But this equality is not true. It's only true if A is a Poisson process, in which case the Poisson arrival C time averages property will say that the arrival average or the event average is equal to the time average. So there is one crucial missing piece, or one crucial piece left that is missing here. And that is to say, how do I relate this expectation? How to relate, and let's keep this general. So I have an expectation 0 to 1 of a function x of t minus dA of t to simply the time average of this function. And again, if you know Palm calculus, you say, oh, this is just the Palm inversion formula. And you apply it and say, that was easy, and go on. It's not hard. It's not hard. But if we want to stick to this elementary view of things, I want to prove it to you now. So for this part, I need my second monitor. I'm going to prove a relationship. Okay. So theorem or lemma or whatever you want to call it. And I'm going to do this in the setting of our GG1 process, but of course it holds in far broader generality. So initialize Z naught, our workload, according to its stationary distribution, and fix F from R to R. I'm going to call it bounded. Okay. Bounded for simplicity for the sake of time, but I'll just make a quick comment of how can we relax this. It'll again be some integrability conditions. F of X, this is the expectation, 0 to 1, 0 U of T, F of X of T plus U, du, dA of T. Okay, so where U of T equals these two things, 0 if no arrival at time t, and this is the next inter-arrival time if arrival at time t happens. So just ignore the equality and focus on this U of T object. Basically, U is, if an arrival happens at time t, U is, this is the next inter-arrival time to be generated, okay? So we have that, tough to parse. So let me draw you a picture. I'm going to draw you a picture, and then this should become a lot simpler for you to comprehend. Here's the picture. Suppose we have an interval, and this interval is, let's say, for simplicity, 0 to 1. And we have some process, in our case, Z of t, or even simpler, just the workload, X of t. This is t. And we observe, should really brought this down a bit. We observe the process, and this, I'm not going to stick true to our workload, that this is our process. The time average is basically saying, I'm going to use this in blue. Time average means I'm going to observe it over this interval from 0 to 1. And it's in steady state. So I'm going to integrate, I'm going to have my expected value, integrate from 0 to 1, x of, or we have the function of x, f of x of t, dt. That's the time average. And by stationarity, this is just f of x. I also have the event average. And suppose my arrivals happen at these red dots. And I can have arrivals happen before time 0 as well. Well, my time average basically says, I'm just going to look at a fixed time interval, and I want to take the average over whatever happens here. My event average says, I would like to observe the process somehow centered or focused around these red inter-arrival times. So how do I draw a connection between the blue and red quantities? Well, you can say, if I observe my process at these red quantities, then what I can basically do is I can look at the average and the, let's say this inter-arrival time is U2. This is the inter-arrival time U1. This is the inter-arrival time U3. This is the inter-arrival time U4. So the inter-arrivals are the time between the events. Basically, if I'm looking at the event averages, I'm going to say I'm going to stop here and I'm going to observe the process until the next arrival happens. And then from here, I'm going to observe the process until the next arrival happens. And then from here, I'm going to observe the process until the next arrival happens. And I'm simply going to add up my observations over these. So it's basically a different way to break up time. Okay, so you observe the process in between these events. Hence, if I go back into the formula, and then the two should be equivalent. Now, if I go back to the formula, this is the time average. Over here, I basically say, so I observe the process from 0 to 1. Anytime an arrival happens, I'm going to look at the process at time t when that arrival happens, and then from t until the next arrival happens, which is from 0 to u of t. So basically, this inner integral is you're averaging the process from the time of the event until the time of the next event. And the outer integral, you're saying, I'm going to look at all of the events to happen in 0, 1. Okay? So hopefully the picture is very convincing. And that is really what is going on. For a proof, let me quickly sketch it out. I do have time. So proof. I want to show, remember, expected value f of x is expected value 0 to 1, 0 u of t. F of x of t plus u du dA of t. That's what we want to show. So we have the event times, and I can write from 0 to 1 f of x of t. This is basically from time 0 until the first event, f of x of t dt, plus from 1 until the total number of events on the interval 0, 1. And it's the easiest way to picture this is, of course, a of 1 could be 0, but just imagine that's a corner case. Just imagine that a of 1 is equal to 10, or a of 1 is some positive number. F of x of t dt, and minus 1 to tau a of 1, f of x of t dt. So this is tau of a of 1 is basically the time of the event, the time of the last arrival prior to 1. Okay. And what is going on basically, just to highlight things, these two things, if you look at the picture here, and I drew, there is an arrival which happens before time 0, before our window of observation. There's an arrival that happens after our window of observation. We, of course, only care about what happens during our window of observation. So we kind of want this left tail, we want to throw it away, and we want to throw away the right tail. But we cannot, because we have to start at some point and observe what happens into the future. In stationarity, the leftover part on the left and the leftover part on the right are going to be the same, distributionally speaking. So this is the leftover part on the right, this is the leftover part on the left. In steady state, these two things cancel out. Okay, so I take just this part. So I got, since the time between arrivals, let's call it u sub m, we have this sum from 1 to a of 1, tau m plus 1, and now it's just a change of variables. dt okay, yeah, this expression is a change of variables, and basically this is what we need to show. Of course, we need to take an expectation, so it means that these two things should cancel out, and they do. Okay, and I think given the time restriction, or given the time constraint, I'm just going to stop the proof right here. let me see if there are any conceptual questions, but otherwise I want to move on to what we can do with this. All right. So we have at a high level, if the proof, went too fast for you or if you missed some detail, just remember at a high level, basically what we've done is we said there is now a relationship between these time average expectations that I'm used to and these event average expectations that we haven't seen so far in Stein's method. And our ultimate goal was to relate the first derivative to the time average first derivative. And let us now see how this is done. So what we have is we have integral 0, 1 f of x of t minus dA of t. What I want is expected value f prime of x. Okay, so we have the inversion formula. This equals integral 0 to 1, 0 u of t, f of x of t plus u, du, dA of t. And okay, right away I see that there is some similarity between these two, but instead of trying to relate this to this directly, let me just do what what is the best thing to do. I'm going to ignore what is written here, and I'm going to pretend that it's what I want to be written here. So in other words, let me add f prime of x of t minus and subtract it. These weird brackets. Okay, so I get expectation 0, 1, 0 u of t, f prime of x of t minus du dA of t, and expectation 0 to 1, 0 to u of t, f prime of x of t plus u minus f prime of x of t minus du dA of t. And this is going to be error. This term, which is not error, I notice that the integrand doesn't depend on u anymore, so I can pull this outside. And I will have expectation, integral 0 to 1, f prime of x of t minus u of t, dA of t. Okay? Almost there. We just have this u of t that is in our way. What do we do with it? Well, this is the inter-arrival time of the person who's going to come after time t, after the arrival at time t. In other words, just like we argued with the service time, this object is independent of this dA of t. That's inaccurate. Like, it's not a mathematically precise statement, of course, but nevertheless, we can pull this out. Okay. And this is just 1 over lambda, 1 over the arrival rate. So in other words, if I take my time average expectation, I do these computations, the time average expectation equals 1 over lambda times the event average expectation that we have. Great. And plus an error term. So long story short, we can take this thing and we can replace it by lambda time. We need to multiply both sides by lambda. We can replace it by lambda times the time average expectation. As long as we can control the error somehow, we're good. We can make this replacement. I want to convince you that the error is controllable in general. So let's focus on the error term. What about the error term? Okay. Let us do just a quick dissection of what's going on. This is time tau minus the time before the arrival. This is the workload after the arrival, but not just after the arrival and some U time units have passed. Because this process is very simple, it's deterministic in fact from t to t plus u. X of t plus u equals the workload at time t, which itself equals x of t minus plus delta s of t, minus delta u. Every time unit that goes by, our workload gets decremented, but it cannot drop below 0, so it's the positive part. And x of t minus is what it is. Therefore, x of t plus u minus x of t minus in absolute values is less than or equal to delta u plus s of t. This is a worst case bound. Okay. Then if we put that back in there, we get an expectation 0 to 1. So let me do this 2 steps in one. So I put in the delta u plus s of t in the integrand, and I'm going to integrate with respect to du right away. So I'm going to get u, I got to pull the delta out, u square of t over 2 plus u of t s of t dA of t. dA of t, yes. Okay, but and we're using this trick over and over and over again, that the inter-arrival time and the service time after the jump is independent of the of what happened before the jump. So I can write this as equals expected value u squared over 2 plus expected value u, expected value s, expected value a of 1. And it is possible to show, it's not very hard, but it's a distraction for us. It is possible to show that this thing is just lambda. So in our particular case, the key that comes out is this order delta, which is needed to ensure that the proper rate of convergence is satisfied. But otherwise, the error of approximating time averages by event averages is controllable, in this case, using the two moments of u and 1 moment of the service time. Okay, so that being said, I think I'm gonna wrap it up. What have we accomplished? We started with the BAR. This is a better place. We started with the BAR. The first part is, okay, easy, that goes into our diffusion generator. The second component, the jump term, needed some care. And in particular, we're going to expand the integrand. We're going to recover that like a Taylor expression like we're used to, except the expectations are with respect to these event averages. Then we ask, is there a connection between event average and time average expectation? And the answer is yes. And in fact, we have an expression, and this expression, this inversion formula, is the workhorse. You're going to go and take each of these event average expectations. You want to convert it back to time average expectations plus some error term, and you want to control the error. Okay. And in this particular example, what you need to do to recover a second order diffusion generator, you need to apply the Palm inversion formula to the first order term once. Then in the first order term, I actually misled you a little bit. Okay. When you do the first order term and you do the expansion and you reach this point, it is not enough just to say, okay, all of this is going to be error. No, because you can do another expansion of the integrand and pull out a second order term. So in fact, this thing is a second order term plus error. You're going to need to take that second order term. You're going to need to apply the inversion formula to that one more time. And then you write the second order term as a time average plus a third order error. Okay, so the main idea is the error should always be third order, otherwise it's going to be the bottleneck term in your rate of conversions. So it's doable. It is tedious, but it is doable. The second term, you need to apply the inversion formula only one time because it's going to give you a second order term plus third order error. Then what you do is after applying the inversion formulas and controlling your error terms, this goes back to our bread and butter. You write down the diffusion generator, you write down the corresponding Stein's factor bounds, you solve for them, and then you compare the diffusion generator with the BAR for the Markov process. Okay, and then you get your error term. All right. I have one last thing to say, but I'm just going to wait to see if there are any questions. So the procedure I've given you it's correct in spirit. It's correct, first of all. And it's if you follow what I've said, the instructions I've said, you will be able to crank this machinery through for the GG1 workload example. Okay, but the GG1 workload is special because it only has we're only keeping track of one residual. What happens if you want to go to models with multiple residuals? Fundamentally, like most of the things I've said will carry over, except for one thing. And this relates to the first order term. So in order for you, so what did I say about the first order term? I said you need to apply the inversion formula, pull out the time average, and then look at this second order term and pull out the second order time average. When you have, let's just call it more complicated models, you are not going to be able to derive an explicit expression for the second order term because the model dynamics are going to be too complicated. What that means is if you try to apply this approach, you're going to get stuck analyzing term number one because you're going to be able to apply the inversion formula one time, but you're not going to be able to apply the inversion formula a second time to the second order term because doesn't have a good, clean expression. So what needs to happen, and I'm just going to leave this term here, and I'm going to refer you to the paper, which is technically still being written. In general, we need to work with what Ziv and I call the compensated. I don't know that it's the best name for it. Workload process. And that is not just x of t, but we have x of t um, at an arrival. At an arrival, we get s time units. So minus rho residual arrival time of t. So this is the compensated process. What is the magical property of the compensated process? Is that it has zero the jump term or the change is equal to zero in expectation on arrivals. So we have if arrival at time t, we have x of t minus, this is the pre-jump, post-jump, x of t goes to x, right? Because if an arrival happens, then the residual arrival pre-jump is zero. X of t plus delta s of t minus rho, and post-jump, we have just the draw from the distribution u. And there needs to be a delta here to match the delta. Okay, so if I take the difference in expectation, let me assume that delta equals 1 just to get rid of this pesky term. X of t minus, we have s of t minus rho u of t, and this equals to 0. Okay, so post-jump minus pre-jump is 0 in expectation. Where does this help us? If we go over here and we consider the first order term, what is the coefficient in front of the first derivative? Well, it's actually the post-jump state minus the pre-jump state. Okay, so this is post-jump minus pre-jump. If we make that to be a mean zero quantity, we are able to kill the first term. And this is crucial. Not only does it simplify the algebra, but it's actually, we don't know a way around it, Ziv and I. Because if you don't kill the first term, you get some kind of very nasty second order term coming out of it that you also have to deal with, but we don't know how to. So anyway, it's crucial to work with these compensated processes instead. And the key defining characteristic of a compensated process is that at a jump, the expectation of the jump of the difference, post-jump minus pre-jump, should be 0. Let me add that, other people working with the BAR also stumbled onto this maybe before us or independently. So this needing to work with this compensated process is a broader phenomenon that others have also needed to tap into. Okay, so these are the main ingredients. We have the inversion formula and the compensated process version. Okay. That combined with our typical generator approach gives you results for models with non-exponential jumps. Cool. I want to switch topics, switch gears, my last maybe 15 minutes, because I do want to highlight what happens for fluid or mean field. Fluid, mean field. And really, I think reasonably you could spend probably another week or two just discussing these things. And I want to give you two names. These two people, of course, they're not the only ones to work on Stein's method. in this context, but in my opinion, they are by far the most consistent contributors and drivers of the whole technology in this direction. Okay. So in fluid mean field, let me give you the general idea of what can even be achieved. Of course, it's like generator comparison. To say how far away is my CTMC, let's just stick to that setting, from its deterministic dynamical system approximation in steady state. Okay. Why deterministic dynamical system? This encompasses both fluid and mean field, but going forward, I'm just going to say fluid because it's quicker. And let me show you what we can achieve back to our infinity example. So I'm not going to do any kind of scaling. So delta equals 1. Remember, we had the Q length and center around the offered load, which is lambda over mu. So I'm going to have x equals q minus r. I'm going to take the Markov chain generator. Let me even say g of q, f of q. This is going to be the arrival rate, f of q plus 1 minus f of q, plus mu times q, number of customers, f of q minus 1 minus f of q. Now, in the same spirit as we done before, do Taylor expansion derive a second order operator? Let's ask ourselves what happens if we do Taylor expansion and use only a first order operator as an approximation. So this will approximately be lambda f prime of q plus mu q f prime or minus f prime of q. And if we look at the uncentered version of the fluid model, so we're basically having a deterministic drift upwards and a deterministic drift downwards. And when motivating the centering, I said we want to solve for the equilibrium point where when is the drift up equal to drift down. So if we don't do the centering, we can still talk about the fluid model, but the fluid model is going to converge to the point Q equals lambda over mu. There's a natural centering always is to recenter that equilibrium to 0. And that's just convenient because we want to, instead of worrying about what is the equilibrium point of the fluid model, we just want to say, no, we always recenter it so that the equilibrium is at 0. So if we have the Markov chain generator, this is lambda. I'm going to do the first order expansion, f prime of x. This is q minus r. Minus mu q, I'll do minus r plus r, f prime of x. And this is just going to be using the fact that mu r equals lambda. This will be negative mu x f prime of x. Okay, so I've taken my Markov chain. I've done first order expansion plus centering to its generator. And notice it's just the first order operator. This is the same drift we had as for the diffusion approximation. But we ignore now the random term. And I can say consider fluid model or deterministic dynamical system model given us by the following: v sub x of t t bigger than or equal to 0, defined by v sub x of 0. This is x. So the sub x is the initial condition. And v dot is negative mu v of t. Okay. This subscript x is unusual if you just talk about dynamical systems, but for us it ends up being like a crucial point. So that's why I'm carrying it around. Otherwise, how did I derive this particular dynamics? I ignore the f prime, and I look at the kind of the dynamic, the first order dynamics of the Markov chain, and I say, okay, I replace x by v of x. So I look at this dynamical system, and this is the first ODE you ever solved. I'm pretty sure that's right, true for all of us. This has a solution, in particular, v sub x of t. This is x e negative mu of t. So it's very easy to solve. The example, the infinite server example, is supposed to be easy to solve. This is the fluid model. We start with some either excess of customers, excess above R, or some deficit of customers below R. So in general, X can be a real value. And we slowly converge to the equilibrium at an exponent, well, not slowly, we converge to an equilibrium exponentially fast. Okay, so far what we've done, we've taken the Markov chain, we've done a first order expansion on it, we've derived some kind of dynamics for the fluid model. We've taken the first order dynamics, we have considered the dynamical system that corresponds to them, and in our particular case, which is very simple, we have a closed form expression, and the expression is very simple itself. What can we do with it? Well, I want to say that conceptually, I don't want to treat this any differently from the diffusion approximation stuff, right? This is a diffusion process with a degenerate random component. We can think of it this way. And so why shouldn't we be able to compare generators, and why shouldn't we be able to compare stationary distributions? Of course, the stationary distribution of the fluid thing, the fluid model is 0. It converges to 0, right? So let us see what happens if we try to compare the Markov chain to the fluid. First things first, we have the Poisson equation for the fluid. And I don't know what I want to call it. Let me call it, I guess, G sub V, F sub H x, which is just negative mu x f sub h prime of x. It's just going to be the first order term equals to negative h of x. Now, assume, this is important, h of 0 equals 0. Why? Because, well, you'll see why. Then f sub h of x is, and this is the potential. I take my fluid system initialized at state x, this is the initial condition, and at time t, and I apply the function h to it, dt. So again, this is basically the same thing as the potential for the diffusion, the same thing as the potential for the Markov chain. The only difference is that there is no expected value because there is no randomness. And now, if you look at this form, maybe you appreciate why we need h of 0 to be 0, because, of course, the fluid model converges to 0. If h of 0 is anything but 0, this integral is not well defined. It's infinite or negative infinite. Okay? Sketch. I could just say, okay, take the potential. How do we know that the potential satisfies the Poisson equation? And the proof sketch is the same thing as we've done before, where I take my potential and I write it from 0 to time epsilon and from time epsilon to infinity. And then from time epsilon, this is basically my potential if I initialize at from state x and I just propagate forward epsilon time units. Okay, so therefore 1 over epsilon, there's a negative part, 0 to epsilon h of vx of t dt equals 1 over epsilon f sub h vx of epsilon minus f sub h of x. And this is d by dt vf of epsilon. So everything is a lot easier in fluid models, right? Because there is no randomness. And this is just the product rule, the chain rule, v dot x of t at t equals 0, f sub h of vx of t at t equals 0. And this is negative mu x f prime h of x. Okay. So this is a quick sketch. I rushed through it because we've done this in the first week. In the first week we did this. But long story short, this is what happens. Let us finally go on to so what? So what? Let's compare generators. We have, for example, the Poisson equation for the fluid, negative h of x. To be concrete, let's say let I'll pick h later. I take expectations, so negative expected value h of x is the Markov chain stationary distribution, and then let me get rid of the negative because I want to multiply everything by -1. Generator Markov chain f sub h of x minus generator of the fluid f sub h of x. And this is order, say, f sub h double prime. There's a lot hidden in that order part, but right, the fluid captures the first order dynamics, and what's left over are the second order dynamics. And we have an expression, and this equals the some test function of h, x, some test function of x. So you look at this and say, oh, well, great, but I'm comparing x to 0. I know 0 is not a very sophisticated approximation, so what can this really give me? And the answer is this is an effective tool to prove tightness of tightness of the, let's say, a family of Markov chains. For example, we take h of x to be the absolute value of x. And so this is the expected value of absolute x. Why is tightness a big deal? And I think I should just stop writing for today. I don't have a lot of time. Why is tightness a big deal? Right? If you've been around in the queuing community the last 20 years, 19 years, tightness is a sought after property because it helps to justify steady state approximations using the limit interchange argument. So, typically people would establish process level convergence to some diffusion approximation, some diffusion limit. But to go from process level convergence to convergence of steady state distributions, one way is to establish a limit interchange. There's this famous box, right? And the major component, the most difficult component to prove in this limit interchange argument is tightness of the stationary distributions of the Markov chains. To show tightness of a family of random variables, it is sufficient, for example, to bound the first moment uniformly across this family, right? So the setting is where the Markov chain depends on some parameters that go to some asymptotic regime, and you want to bound the expectation, let's say, uniformly in terms of these parameters. And so far, I've been promoting the use of, let's say, Foster-Lyapunov criteria or Lyapunov functions to do this using some kind of drift inequalities. Another systematic or promising way that you don't really have to guess at the Lyapunov function is to use this fluid potential. And long story short, if you pick h to be this absolute value of x, then you can use the fluid potential as the Lyapunov function, provided you have control over its second derivatives. You can basically, the tighter your bounds on the second derivatives, the tighter the bound on the quantity of interest that you're going to get. So outside of tightness, I mentioned a lot, we need moment bounds, right? For Stein's method, we need moment bounds, like bounds on the moments of these distributions. That's another use case for the fluid machinery. So if you can't find a Lyapunov function, it's very difficult, then maybe the potential will offer some tractability. Small technical note that I should mention. Actually, technically, so remember how in the generate diffusion approximation setting, I said that the regularity of the Poisson equation solution depends a lot on the regularity of the test function h. In this example, if I take h to be this function with a kink in it, right? Actually, the second derivative of the fluid potential is not going to exist at the origin. So a common approach or a common trick is you want basically to smooth the absolute value function. So outside of the origin, it is linear like we expect it to be. Here on the origin, it should be smooth. Then you can get regularity. Then you can get the second derivative to exist everywhere. That's one little technical nuance. A second and very important technical, not even a nuance, but a big technical consideration is I have so far made it sound like deriving a closed form expression for the potential is simple. That's not true. Okay. This has, if you take h of x to be the indicator that you're outside of some set of the origin, then what this is, it's like the hitting time of the fluid model into some compact set of the origin. Well, hey, that's the theory of stability, right? That has deep ties to the theory of stability of stochastic systems through or via the fluid model stuff. So there's a deep connection between let's say using an indicator test function. All this to say the connection exists, and we already know that the stability stuff and the stability issues are non-trivial, highly non-trivial. So in most of the time, it is highly non-trivial. You usually will not have a closed form expression for the potential. Even when you don't have a closed form expression for it, you may be able to derive some kind of bounds on its derivatives. But in practice, this has shown to be this is a tedious process, in particular because it requires you treating your state space as separate components or separate parts of the state space. Why do we need to do that? Because the fluid model doesn't need to visit the entire state space because it's deterministic. Okay, so that's roughly why we end up dividing the state space. So you see, you can spend 2 weeks on this easily. Not going to. Read the follow-up papers and reach out to me if you have any questions. All right, so I'm going to steal a couple of more minutes just to conclude this. All right, so what we've seen over the past 5 weeks, I like to think of it as week one. This is the preliminary stuff. This is what, most researchers who have graduated or who have their PhD, week one, maybe 80% of it is known, unless you're from a distant field. Week two and three, and we spilled over to four a little bit. This was really the core package, the generator approach and the prelimit approach. I want you to think of these things as duals of one another. Sometimes one approach will be preferable over the other, but they both contribute something. And in the last little while that we've covered what I'll say more advanced topics, multi-dimensional settings, the theorem from, say, Gilbert and Schrödinger, via Tygurovich's a little foray into general primitives, just a word on fluid models. And my last thing I want to mention is, like, where do I see all of this going? To be honest, there are some technical questions which are still, I think, of interest that we didn't even have time to get to here. But I'm gonna call it that this machinery, in my opinion, has now sufficiently matured where it is harder for me to see novel, like huge methodological breakthroughs, as opposed to great applications of this stuff to say something meaningful about the problem that you're solving. So put it that way. And that's why I'm doing this course. I hope to just proliferate the stuff. It's a fairly complete theory at this point. And of course, if you think about the broader Stein's method community, this is just the tip of the iceberg because there's like 100+ people working on Stein's method in a whole variety of settings. Yeah, so it's very interesting. There's a lot to it. All right, I really appreciate the audience. I appreciate the cameras, Diego and Ziv. Thank you for the opportunity. And I've already gotten an email that somebody's been watching the YouTube videos. So that's all that at least one person. Yeah.
All right. Thank you, Anton, for both this lecture and the entire course. So just to sort of reiterate, so we hope you've enjoyed the sort of SNAPP summer school. Obviously, if you have questions about the material, you should reach out to Anton. If you have any feedback about sort of kind of the meta level course stuff itself, even if it's just, I liked it and I'd love if Snap did this again, that's really useful for us to hear. So please feel free to send me or the Snap email a note if you have sort of thoughts. And finally, so the videos will remain up on YouTube and linked from the Snap website, and we'll get the last few lectures and notes as posted soon as well. All right, so with that, thanks again, everybody, for attending.